Thank you. Thanks for the invitation. It's a pleasure to be here. I will be presenting today a joint work with Guillaume, Cébron, and Mireille, Capitaine that will appear soon. It is on the strong convergence of multiplicative Brownian motions on the general linear group. So I will start by a little introduction leading to this problem, and I will try to do a parallel comparison between the self-adjoint case and a non-self-adjoint case. So start by the GUE, and we know by Wigner's theorem that almost surely mu, if I say I'm going to call it a mu n, converges to the semicircular law weakly as n converges to infinity. And on the other side, we will have the G-Niebuhr model, and which says that almost surely the same thing happens, but the limiting distribution is now the circular law. Okay? So on the light of the central limit theorems, we can think of these models as the sum of large number of matrices that are small and that are identically distributed and independent. And it's also useful to think of these matrices as the endpoints of some Brownian motions. So we're going to think of the GUE. We're going to see it as the endpoint, let's say H1 of the Brownian motion. I'm going to put here n to say that this is an n by n matrix. HNT greater than or equal to 0, that's starting at 0 and variance T over n. And I'm going to call this the Wigner Brownian motion. So this has independent additive increments. So HT
the variance of the matrix?
T over n.
I don't know what the variance of the matrix means.
This is not, oh, okay, so this is defining the entries.
The entries.
Yeah.
The variance theorem.
Yeah.
Okay. Yeah.
Okay. So this to be stationary and stochastically independent. Okay. And on the other side, there will be the G-Niebuhr Brownian motion. And we can also see the G-Niebuhr matrix as the endpoint of this Brownian motion that I'm going to call CNT, also with Cn0 equal to 0, same thing. And we can write CNT as 1 over square root of 2 of H NT plus H tilde NT, where here we have independent copies. Okay? And this, I'm going to call it the G-Niebuhr Brownian motion. So Valkolisco proved in 91 proved the following. Again, I'm going to divide my board into two halves. That Hn of t converges to little xt. Now I'm going to tell you what this is. As n tends to infinity, and this is also almost sure, but how is this convergence defined? It is infinite, non-commutative, finite-dimensional, non-commutative and commutative distribution, meaning that for all n and n, and for all t1, tn that are positive, we have the following. The limit as n tends to infinity to 1 over n the trace. You take any polynomial and hn t1, hn tn. This equal to tau, in some non-commutative probability space, of the same polynomial in xt1 up to xtn. And this is for all polynomial in 2n indeterminates. Okay? And this little x is what we call the free additive Brownian motion. Okay? And of course, from this, we can directly conclude the same result for C and T. Okay? So we can prove that converges to, I'm going to call it C, T. Also, almost surely, as n goes to infinity, and here Ct, it's again 1 over square root of t, xt plus I, xt tilde, where these are freely independent, free additive Brownian motions. So this was the result of Valkolescu in the additive case, and it's natural to think of the multiplicative case, okay? If we would like to think, for example, of product of independent matrices that are close to 1, let's say, or multiplicative Brownian motions. So it's useful to note that these can be seen as Brownian motion on the unitary Lie algebra, and this one on the general linear Lie algebra. Okay, and there's a natural way if once we, with respect to if we consider this as inner product and the real part of the trace of A star B, there's a natural way to get Brownian motions, multiplicative Brownian motions from this here. And this is, in this way, we can define unitary Brownian motions on the unitary group and on the general linear group. So on the unitary group, and on the general linear group, I'm going to write UN and CL and C. Okay? So this is done by something called how we pass from these Brownian motions to this by the stochastic exponential map or the rolling map. And what we get is the following. Need always to look to write the name. Stratonovich. Stochastic differential equations. And we define the unitary Brownian motion to satisfy the following stochastic differential equation dHn t minus half unt dt, and starting at the identity. And here in this case we have.
This is the Stratonovich or Ito? This is an Ito equation, right?
Yeah, but this is how they call the stochastic differential equation.
It's very confusing because the Stratonovich should have a Stratonovich equivalent.
Yeah, I don't know.
But it's an Ito equation that you wrote here, right? Otherwise, I don't think you would have the second term if it were Stratonovich.
Yeah.
So it's an Ito equation. Good. All right.
Yeah, I think so. Yeah. Okay, so T, and here again we are starting at, here 0 at the identity. Okay, so this is the unitary Brownian motion. And this is the general linear Brownian motion, or the multiplicative Brownian motion. So similarly to what happened here, if we want to look at the large n limit for these Brownian motions now, since they are defined as solutions to this stochastic differential equation, it makes sense that the large n limit of these Brownian motions will be some Brownian motions satisfying similar SDEs, but with the HT here replaced by its free limit, and Cn here replaced by its free limit. And this is what Bian introduced. So Bian introduced these property, these Brownian motions, so called the free unitary Brownian motion, to satisfy exactly the same thing, but with this free additive Brownian motion instead of h, minus half ut dt. And here u0 is 1. And in the same way, we have d, call it, no, I will stick to b, bt, which is bt dct. And d0 also 1. And what Bian proved, he proved the parallel result of Valculescu. So Bian, in this case, in the unitary case, proved in 1997 that indeed un t converges as n goes to infinity to ut almost surely, but he proved this in the case n equal 1 and t1 equal to t, so for fixed time t. And in this case, because you want to keep those, so I will hide them for now. And in this case, because n is equal to 1, we know that the inverse is the conjugate. And this problem reduces to proving the statement 1 over n, the trace u and t k converges to dou of u t k. So here, Bian was able to find the moments, but from the moments, in this particular case, we're able to determine the limiting measure, okay? So from these moments, he was able to completely determine the measure and study its properties. And he conjectured, so here I would write that he conjectured that the similar thing would hold for the general linear group, okay? So he conjectured that P and T will converge to Bt as n goes to infinity almost surely. And this was proven for fixed T by Cébron in 2013. So fixed T. But since the left multiplication increments of these are independent and stationary, there's a way to make it for T1 up to Tn. And then it was proving in the full generality by Todd Kemp in 2016, where he gave a unified proof for these two situations by introducing a family of Brownian motions with two parameters. And he proved this result for this family with two parameters and for times T1, Tn. Okay? So he gave a proof for a family with 2 parameters that encompasses both cases. And for T1, Tn. So it's worth mentioning that these two are connected through something called the Segal-Bergman-Hall transform. And they are related to things in Yang-Mills theory, but I'm not expert on this. But people are very interested in studying such Brownian motions and seeing their what happens for their large n limit. So just a very important note here that unlike the unitary case, even if you prove the convergence in non-commutative distribution, you only find the moments. But because this is a non-normal operator, we cannot say anything yet on the limiting eigenvalue distribution. So this is still an open question, okay? And the good candidate, however, is the Brown measure of BT of this. I didn't write its name, so this is the free multiplicative Brownian motion. Okay, so the good candidate for the limiting spectral or the limiting eigenvalue distribution is the Brown measure of the free multiplicative distribution, but this hasn't been proven yet. However, the Brown measure has been studied a lot and studied its property and its support. And I should just at least mention the name of the some of the people. I apologize if I forget some. And Zong, who's here, the audience. So this has been studied, its properties, and they have descriptions of the support and all that. Now, in a paper in which year I didn't write down and I forgot. So in one of their papers, Driver, Hall, and Kemp considered, there's a family of Brownian motions with 3 parameters. I will write it down. This will be the model that we will study. And they proved in this paper that this is the most general family over the general linear group. Okay, so this family with 3 parameters, and this is what we will be studying. So now it's time to introduce the model that I will be considering. So I will write here the model. So we're gonna let theta be in R, A greater than or equal to 0, and B greater than or equal to 0. And we're going to set lambda to be A squared plus B squared, and tau to be lambda minus exponential I theta A squared minus B squared. And we call the rotated elliptic Brownian motion the following. So it is defined by Zn and lambda and tau time t. This is Ei theta, A, H, and T. So this is the Wigner Brownian motion plus I, B, H tilde, and T. And of course, these are stochastically independent. Wigner-Brownian motions. So I will tell you what these parameters mean.
The free unitary is also a specific case of that?
Yes. So this family, if you change the parameters, you would recover the unitary and the multiplicative case. And this is the most general thing you can define. Okay, so this is what they proved in this paper. So these parameters correspond. Lambda is 1 over n expectation of the trace of z lambda tau of 1 star. Okay. So this is the positive variance. And tau is defined by the same thing, but we subtract from it the trace of one squared. And this is the complex covariance. And this is well defined. 1 lambda minus tau is less than lambda. So this is how we define the rotated elliptic Brownian motion. And as we did before, we're going to, from this, define the one on the general linear group. So the multiplicative lambda tau Brownian motion, it's not the same g like before, so that one was that I defined earlier. So from now on, g will be this one, but should have maybe chosen is the solution of the following. This IG and minus half lambda minus tau gn lambda tau of g dt, and it's starting at 0 at the identity, sorry. And now I give a remark to show you that for particular choices of lambda and tau, we get the unitary and the multiplicative one. So if we take lambda tau to be 1, 0, we obtain the unitary. And if lambda tau is equal to 1, 1, we obtain GT. So these are particular cases of this general family. So here, this parameter controls the overall diffusion. The real part of this controls the diffusion in the unitary, the unitary diffusion, and the complex the imaginary part of this will give you an idea about the correlations between the unitary and the free one. And in the same way, I can define the free one. So I'm going to call it a GT. Maybe to gain some time, I'm going to add here free. And I'm going to call it little g of lambda tau of t. And here I just replace this by small g. And here I will tell you now what is this little zt. And here this is by, I'm going to also drop the coefficients lambda and tau. You know what? So this gt, I will stop writing the lambda and tau of t, and I will simply write it to g with subindex t. So it satisfies the same equation, and here g0 is 1. Okay? And what is this little zt? So it is like before. It will be similar to the rotated elliptic Brownian motion, but the free version of it. So axt plus ib xt tilde, and these are freely independent additive Brownian motions. And now it's time to state the result. So we're going to prove strong convergence for this model. So in order not to keep always repeating the same thing, I'm going to, for any t0 greater than or equal to 0, I'm going to write gt to be gt star. So also I'm dropping the lambda and tau, so I'm not talking anymore about the g that I defined at the beginning. It's really this 3-parameter family, but not to repeat the parameters all the time. gt inverse and g inverse star. And I'm going to put n here to remind you that this is an n by n matrix. And similarly, little gt, so this will be gt star, gt inverse star. And what we prove is the following. I want this, yeah, I will write it here. So what we prove with Guillaume and Mireille. So it's still, it will appear soon. Prove the following. With the right choice of lambda tau so that everything is well defined. And for all n greater than or equal to 1, and for any polynomial p in how many determinates here? So p, 4p per determinates. And for all little n or little p greater than or equal in n times t1 to tp that are greater than or equal to 0, we prove these two statements. Almost surely, first we prove the weak convergence. The limit as n goes to infinity of 1 over n, the expectation of the trace of p in gt1, gtp, minus tau of p of gt1. Maybe I should put a line here. GTP. Oh, I put the limit there. Okay, so this is equal. And the strong convergence for this. Okay, so it's worth noting that this is going to be the main focus of the paper. This result is also new for this 3-parameter family, but with an adaptation of what, for example, was done for the 2-parameter family, one can still prove it. But for quite some time, most of the results were in expectation. And after some results of Camp on getting estimates on the variance to lift these results to asymptotic, to almost sure, we started to be able to get such, this convergence almost surely. And this is going to be the main part of our paper proving the strong convergence. So, but, sorry? Oh, yeah. Thank you. So also this result on the variance, which is of independent interest, because to study SDEs, people are interested in certain classes of functions and would like to understand how the variance of functions of these polynomial behave. So we also prove if we have h to be a C3 differentiable function, with compact support, then the variance of the normalized trace of h of p star of GT1, GTP is of the order 1 and 4. So in order to prove strong convergence only, we could have ignored here to take the inverses and proving the result only for GT and GT star, and then using a result of Cheng-Yin from 2018 that says that if you have the strong convergence for polynomials, you can pass it to rational expressions in them. Whenever the rational expression is well defined for the limit. So we could have just not bothered about these two terms, and we would still give the same statement. But in our proof, we decide to still consider them because we want to prove such a statement too. And here we also want that our statement be valid when we have the inverses. Okay, so just a technical remark. And now in the 5 minutes left, I will tell you a little bit about the proof. What should I raise? Maybe here. So to prove the strong convergence here, there's a first trick that we do in order to, using the fact that the multiplicative increments are stationarily and stochastically independent, to reduce the problem. Instead of having it for multiple times, t1 up to tn, we'll have it for a fixed time t, but then we're considering processes that are independent. So this is the first thing we do. And once we do this, our problem, now you can think of a GT that I just erased. Instead of being at times t1 up to tp, it will have independent Brownian motions, okay? So once we do this, we would like to prove, like idea of the proof, we would like to prove that the expectation of the normalized trace of some function of pp star of gt, okay, minus the same thing but for the free Brownian motion. This is of the order 1 over n squared. And once we have this result, in order to pass to almost sure convergence, we're going to use this bound on the variance. So using the bound on the variance. Once we have proven such a statement, if we choose f to be equal to 0 in the support of this term, then we have proven strong convergence. And these are classical ideas that hopefully someone will explain more in details. Yes?
So what dependence on f do you get in these O?
I will mention now. And in order to get rid of this f, we're going to use alpha strong. No, it's AJ. Representation formula. That changes this problem from studying functions of these polynomials to studying their resolvents. So we have to prove that for all z in C+, the expectation of the normalized trace of z minus pp star of gt inverse minus the same thing for the free multiplicative Brownian motion. Okay, and then of course the bounds that we obtain from the from this approximation, they will have some terms that have 1 over the imaginary part of that to some power k. And then if we obtain this, then we need our function to be ck plus 1 differentiable. Yes?
P star of gt, is that just some non-commutative polynomial
Yes.
multiplied by its?
No, it's a non-commutative polynomial.
Multiplied by its adjoint, yes.
Multiplied by its adjoint.
Yes. Okay, so it reduces our problem to proving this, and here we use the interpolation. So now, because recently there have been many techniques that will be discussed in coming talks, but here not all the techniques work. For example, if we do the expansion of this, we cannot write it as a rational function. So we follow ideas from the work of Collins, Guillaume, and Pau. Okay, and the main thing one needs to. May I take 2 more minutes? So maybe this is the most interesting part for many of you. So one would want to notice that if we consider this, now this is an mkn of c-valued stochastic process. Okay? It has the same distribution if we take it with respect to the normalized trace of nk as if we consider our original Brownian motion with respect to the normalized trace with respect for n. And now we introduce a Brownian motion k t that satisfies, unfortunately I have hidden, I'm going to show you quickly, that satisfies, oh, it's the wrong board. Where did I write? Oh, perfect. That satisfies this equation, but here we take the opposite sense of multiplication. Okay, so just we exchange here these two. And so this is nk. This is, and if we take k goes to infinity, then we know that the limiting distribution of this is gt. Okay? And if we take here the limit of this to go to infinity, we will get gtn. Okay? And this is how we do. And then the interpolation will be is done in a multiplicative way, not in an additive way, between k, t, and k, and identity tensor g and t. Okay? And how do we interpolate? We're going to consider psi u to be, it doesn't matter the order, but okay. Tn, t minus u, k u. And you can see that whenever you have u equal to 0, you obtain this process here. And for u equal to t, you obtain the k. And we interpolate between these two, but this is a multiplicative interpolation. And it's so not straightforward. Like, it's not that if we follow what was done in the additive case, things will go there. So, and we need to rely, of course, on Ito's formula and look at the differentials and at the brackets of all these terms in order to interpolate and finally get these bounds that we have. So it was very vague on the proof, but if you have more questions or if you're interested to know more, we can discuss afterwards. I will stop here.